I have the UPS back together now, and it's time to find out if I improved it or if I broke it. So I have my batteries over here. They should be pretty well fully charged. It's not plugged in right now. I have the UPS plugged into this power strip. That lets me turn it on and off quickly in case something goes catastrophically wrong. And I have two meters, one plugged into the outlet measuring AC voltage, which is why it's 0, and this one here measuring the battery voltage, just like before when I was checking the efficiency. I have one connected to the heatsink, which is the positive terminal, and this one just connected to case ground. So the first thing I'm going to do is, this is reading 8 volts on the input because there's some residual charge yet in these capacitors. But the first thing I'm going to do is take my power plug from the batteries, my 8 gauge plug here, plug it in, and nothing terrible happened. Apparently my battery bank is at 26 volts, it's about 13 volts of battery, so they're definitely fully charged. And I'll turn on the AC power, see what happens. Okay, my battery voltage is going up to about the right voltage. It's not overcharging the batteries or anything, yet it is charging them, so that's a good sign. Transistors aren't getting especially warm, nothing unexpected anyway. So I think it's time to try turning it on and see what it does. I have 120 volts on the output. I'll switch over to battery here. And I still have 120 volts running off of the battery. So it seems like it pretty well works. So that's a good start, but the first thing that I want to do is to redo that efficiency test. If the efficiency is higher than it was before, that's obviously a good sign. If it's lower than it used to be, then that means I messed something up by replacing these, and the unit's actually getting hotter than it was before I made any changes. That wouldn't necessarily be catastrophic, but I wouldn't be happy about that. So everything still seems good. So everything is pretty much the same way as it was before when I was doing the efficiency test, the initial preliminary one before any changes. I have the same battery bank connected up in the same way. I have two 60 amp fuses here, fusing my two batteries together. That's probably pretty important. If I short circuit these batteries because of some internal fault, I don't want them spraying battery acid all over. That could be bad. Through my about 4 feet of 8 gauge cable here, and yeah, everything's pretty much the same. So I'm going to set this thing up on the tripod. Amps zeroed out. I'm just going to clip it around this wire this time. So it looks like it's charging the batteries at 1/2 amp. I'll shut off the AC power. And it takes 1.9 amps at 26 volts right now. So I'll write that down. That's what it takes at idle. That's a little bit higher than it was before I made any changes, which is to be expected. The no-load power draw is probably going to be a little bit higher. I think it was 1.7 amps if I remember right. Oh, I have it right here. 1.6 amps. No load before. Now it's 1.9. So I'm using 300 milliamps more. It's about what I expect. There's more more capacitance in these transistors. That has to be switched now that there's twice as many, so that'll take a little bit more power. So now I'll turn the fan on, the heater onto the fan function, just to make sure that nothing terrible happens. Low. And now it's on medium, just like before. So I'll wait for the voltages to stabilize. And we are at 23.9 volts and 43.4 amps. And for good measure, I want to check the output amperage draw also. It's telling me 7.1 amps at 119 volts. For some reason it's not going down to 0 when it's not connected. So I think I'll have to subtract about 0.2 amps from that to zero out the calibration. But turn it back on so I can charge the battery. And just out of curiosity here, I want to know what it's doing to the battery charge current. It's charging the battery at 7 amps. That's quite a bit more than it did before. So that's kind of interesting. It actually charges the battery faster now. Anyway, I'll run some numbers and get back to you here. So after running the simple calculations, I find that it took, before I made the changes, it took 42 watts at idle, and now it takes 49 watts. So it takes a few more watts at no load. But with the heater on, the output voltage is identical, so I'm just going to use the same output wattage as last time, since I'm sure the heater didn't change and my meter seemed to be a little bit off calibration. So the output wattage I'll assume is the same. The input wattage to the UPS from the battery this time was 1037 watts, and last time it was 1039 watts, which is within tolerance of measurement error. So basically the efficiency of this unit is the same as it was before I started, and I have to say I'm a little bit disappointed in that. I thought it would be higher. It might have something to do with the transistors I selected, or with the gate drive resistors that I put on there, the 0 ohms. Maybe I should have put on 20 ohm resistors. I'm not exactly sure, but in any case, the efficiency is about the same. So there is one thing more that I want to check. I'll redo the thermal performance test like I did initially to see if that shows me any different results than the efficiency test. I assume it won't. But also I'm curious about the surge current rating. The surge capacity may still have been increased with these new transistors, so I think I'll do that test next. I'm back with my disgusting looking dehumidifier over here. That will be my stand-in for the proper equipment, since I don't have the proper equipment to measure surge capability of a UPS like this. But I want to redo the surge current, surge wattage capacity test of this using this same dehumidifier in the same configuration as before to see if I did indeed improve this or not. Apparently the efficiency didn't improve, so we'll see if this did. But I have it plugged into the wall. It's running off of wall power right now. This is the output voltage, 122.6 volts, which is our wall voltage right now. And this is the amperage, AC amperage going out to the dehumidifier. So I'll power it up off of wall power. Kind of take a baseline, and we're looking at a little over 6 amps to operate this. And I'll do another lock rotor current test here by shutting it off briefly and then turning it back on. So we're looking at 33 amps at 107 volts. And that is exactly the same as the previous test. So that's a good baseline. To kind of recap from the first set of tests that I did, it was 33 amps at 107 volts. So that means that the wall voltage sagged to 107 volts under that 33 amp load. If you multiply the two together, you get 3,500 watts. When I was running off of battery power, the output voltage of the UPS sagged to 80 volts, and this unit only drew 22 amps, which yields a surge capability of about 1,760 watts. So now I'm going to shut off the wall power, let it run off of battery power. It's running off of battery power now, and I'll redo this to see if the output capacity is improved or not. Well, I saw it go up to 30 amps, but then it shut off. Not quite sure what that means. Take you off the tripod here. So if I look at the front of the unit, it has a single LED flashing for the battery level. That indicates that it thinks the battery is dead. However, I know that this battery is fully charged. So this doesn't look like a fault condition. I'm wondering if my battery cables potentially aren't heavy enough. Let me do one more test here quick. Get you back on the tripod. Instead of clamping around the output, let me clamp around the input wire. So now I have the meter clamped around the input battery cable. I'm going to just reset this. Okay, turn the unit on again. It's drawing 1.6 amps from the battery bank, which is less than I measured previously, so perhaps it doesn't actually take more oil power. I don't know. Maybe that could again be a measurement error. But anyway, I'm going to set this for peak, and it'll record the peak amperage draw now through that cable. And I'll turn the dehumidifier on in a minute. Okay, it started up that time, and it says 187 amps, which is way higher than it used to be. Let me try that again. Yeah, it shut off that time. Okay, so 187 amps is quite a bit to be shoving through 4 feet of 8 gauge cable and such. Let me look a few things up and I'll come right back here. I looked up a basic American wire gauge table and found that it's very possible that my cables here aren't adequate for a 200 amp draw, even a momentary one. I have about 1 foot of 10 gauge wire here coming from this connector into the UPS. 10 gauge wire has a resistance of about 1 milliohm per foot, and there's 1 foot in, 1 foot out, so that's 2 feet. At 200 amps, that's 0.4 volts of voltage drop. There's a connector here. There's probably some more drop in there. I don't know how much. I'll just call that 1/10 of a volt. So we have 1/2 of a volt of loss here. And these cables going into the input are approximately 4 feet long, and there's a run out and a run back. 4 feet of, or I should say 8 feet of 8 gauge cable at 200 amps is 1 volt of voltage drop. Plus I also have some drop in these fuses, in the cabling between the batteries, and of course the batteries have an internal resistance as well. So I'm looking at least 1.5 volts of voltage drop just going into this UPS. So I want to try to reduce that to make sure that I'm not just dismissing this unit as having a problem before I improve that connection. So I found some 6 gauge wire here, just a length of 6 gauge wire. Then I'm going to jumper in to replace some of this lossy wiring, the 8 gauge and 10 gauge combination, which isn't adequate. So we'll try 6 gauge. There's no easy way to connect the ground without making some modifications here. So if this improves it, I think I'll just cut this wire and put a splice in, a good splice, from this thin wire into something fat like this, 6 or 4 gauge, to run out to the batteries eventually. But for now I'm just going to leave the ground connection to the batteries as is and improve the positive. So that'll get me 1/2 of the way there, and hopefully that'll be enough to demonstrate. Alright, so instead of doing something fancy here, I think what I'm going to do is take, since I know that these heat sinks here in the middle, discharge the caps quick. These heat sinks here in the middle are positive. I'm just going to take a pair of vice grips and clamp a wire on this wire onto there. Maybe this side will work better. I have this side vice gripped onto the positive heatsink, and this side vice gripped onto the battery. So that'll be good enough for this temporary case here. Turn my voltage back on. I think everything's good here. Nothing should be shorted out. So I'll plug this in. It all looks good. Try turning it on. That still works. Alright, let's retry the test. This is on AC amps. Turn the dehumidifier on. It runs. Now let's see what the surge is. And it did work that time. So this went up to 30.5 amps. And my output voltage sagged to 105 volts. Okay, so 30.5 amps at 105 volts is 3,200 watts, which is an enormous step up from the original 1,760 watts. So adding the transistors may not have improved the efficiency, but it did drastically improve the surge capability of this. Putting this 6 gauge wire on here helped significantly. So it does need that now that the FETs are upgraded. I'll have to also upgrade the negative cable at some point, but this does tell me that it needs better power from the batteries to operate properly. It's also interesting here to note that the power coming out of this is just about as good as coming out of the wall. When it was being powered by the wall outlet in my house, it caused a voltage droop down to 107 volts from the power company, and the UPS itself droops to 105 volts. So it probably has a surge capability if I upgrade these other cables and put on a heavier load of well over my tested 3,200 watt level, but that's good enough for this. This will be enough to start at just about any load in a house. And out of curiosity here, I also want to check one more thing. I'm going to take my clamp meter, put this around my battery cable. Let's see, I can't clamp it around the positive one. I have to put it around negative, because my positive is now split between 2 different wires. So I'm going to put it around that one. I'm not sure if you can see that on camera, but move the camera a little bit. Maybe that'll help. I think you can see that. So that's the DC amps coming into the unit. Zeroed out, so it's actually correct. And I want to see how many amps it pulls from the battery now under a surge condition. Yeah, and right around 200 amps. So this draws 200 amps out of the batteries when it's putting that 3,000 watt surge out there. I'd also looked up the ampacity of some of these cables in here, turn the AC power back on, of 10 gauge wire, and the ampacity of that is 55 amps for chassis wiring, which is what this is, And 55 amps at a 24 volt battery bank corresponds to about their 980 watt original limit as rated for this unit. So that's probably why they chose to use 10 gauge wire. It just barely met the specifications. But it's not good enough anymore, so I'll have to upgrade that. I think the next thing we're going to do is make a few other changes to this. It's still currently going to be limited to 980 watts. After that it'll detect an overload and shut off. And it also has that annoying beeper, so we're going to fix both of those issues next.